Now that we've been introduced to the concept of curvature, I'd like to introduce another curvature formula, which is potentially really helpful if you don't feel like taking the derivative of a unit tangent vector. So this curvature formula states that starting with r of t, if you take a derivative, followed by a second derivative, cross those two vectors together, find a magnitude, and then divide by the magnitude of r prime of t, quantity cubed, that is another way to find the curvature formula. Now, with that in mind, we are going to go over the proof of this. Now, for the purposes of what we're doing in the proof, I'm going to go ahead and stop writing of t, and we'll just assume that everything is a function of t. So, for example, our unit tangent vector is what we got by taking r prime and then dividing by the magnitude of r prime. What I'm going to do is reorder this slightly so that I can avoid the use of the quotient rule for the purposes of what we're doing with taking another derivative. So what we're really saying is that r prime is equal to the magnitude of r prime times unit tangent vector. Now, trying to take the derivative of something that's already a magnitude doesn't sound that much fun. However, we did show that the derivative of the arc length formula is the same as the magnitude of r prime. So we're going to refer to that as s times t. Excuse me, s prime. S prime is the same as the magnitude of r prime. So what I'm going to do is take another derivative, and this will be r double prime. According to the properties from the previous section, since we're taking a scalar function times a vector function, we can apply the product rule. So this will be s double prime times t plus s prime times t prime. Now, this doesn't tell us a whole lot, but I do want to point out, though, that t prime is part of the curvature formula, so it's good that we see it in there. Now, as part of our formula up here, we're supposed to take r prime and cross it with r double prime. So we're going to take r prime and cross it with r double prime. So r prime, cross it with this thing that we have here. Now, with that in mind, it looks like we are now officially dealing with, well, what looks like a lot of stuff. What we're going to do is use some properties of the cross product to see if we can work through a couple of these things. So first thing I'm going to do is re-express r prime using this fashion up here. So this will be s prime times t crossed with s double prime times t plus s prime times t prime. Next, we're going to use the fact that this is a product, so it does distribute. I'm going to start using parentheses so that we can kind of see what's going on here. Crossed with s double prime times t plus s prime t crossed with s prime t prime. Next thing that I'm going to do is remove the scalar multiples from the cross products and put them in front. So for the first guy here, we are referring to s prime times s double prime times t crossed with t. That's using the associativity of scalars with the cross product. Plus, this will be s prime squared times t crossed with t prime. Now, some interesting things are about to take place here. Specifically, when you cross a vector with itself, you wind up getting the zero vector. So this right here will be equal to the zero vector, which is why I'm going to stop writing it. Now, when it comes to the unit tangent vector, I would like you to recall that it is guaranteed that the magnitude of the unit tangent vector is equal to 1. And what's important about that is the fact that that thing is a constant. Now, as a reminder from a previous video, if the magnitude of a vector is a constant, then it will be orthogonal to its own derivative. That is important because we're taking the cross product of something with its derivative. What this means is, if I were to consider the magnitude of r prime cross r double prime, this is going to be equal to, the first term is dropped out because of the zero vector, and we're going to see an s prime squared. We don't need to apply the magnitude to that since it's already positive and it's a scalar. And we're going to wind up with this. This will be s prime squared times the magnitude of this cross product. According to the magnitude of a cross product formula, this is going to be s prime squared times the magnitude of t times the magnitude of t prime times the sine of the angle between them. But according to that property that I just showed you on the other page, t and t prime are orthogonal to each other. So theta is 90 degrees. Additionally, the magnitude of t we just said is equal to 1 because it's a unit vector. So we wind up with the following. That s prime squared times the magnitude of t prime, this becomes 1 and this becomes 1. Now, if you'll recall though, s prime is the same as saying the magnitude of r prime. So this will be the magnitude of r prime squared times the magnitude of t prime. Now with that in mind, the curvature formula that we previously had is that this will be the magnitude of t prime divided by the magnitude of r prime. If we substitute in the fact that magnitude of t prime is now equal to this magnitude divided by this magnitude squared, that allows us to conclude that the magnitude of r prime cross r double prime divided by the magnitude of r prime, we have a square from here and one additional one from here, that is cubed. That completes our proof. Do you have to know the proof? No. Is it good to know the proof? Yes. What's more important to know is a situation where you would want to favor one formula over the other. So with that in mind, quick discussion about our three curvature formulas and when to use which. So we had the magnitude of dt over ds. We had the magnitude of t prime of t divided by the magnitude of r prime of t. And we had the magnitude of the cross product of r with r prime divided by the magnitude of r prime quantity cubed. So, this one, when do we use it? Given that the first step is to reparameterize with respect to arc length, that's already a gigantic pain in the butt. Don't even bother. Now, regardless of which one of these two formulas you're going to be using, there is a very clear first couple of steps. First step is going to be differentiate r. Next up, find its magnitude. So at this point, you have created r prime as well as the magnitude of r prime. Both of those are used in both formulas. Now at this point, this is where you can make a little deviation. One of them is going to be find capital T. You find capital T by taking the derivative that you just got and dividing it by the magnitude that you just got. What is almost guaranteed when you do this is you are almost guaranteed to wind up with quotients. Therefore, in order to use this formula, where we find the derivative of this thing, it's almost guaranteed that you use the quotient rule. There are certain situations where it won't happen, and in those situations, I recommend that you go this route. So if you have to use the quotient rule from here, if the answer is yes, or excuse me, if the answer is no, use that formula. I'm not saying never use the quotient rule. What I'm saying is that there's enough going on in these problems where if you can avoid using the quotient rule, try not to. If the answer is yes, you would have to use the quotient rule, punt on that and just go ahead and find our double prime and then use this formula. So given that the process starts the same way anyway, you're allowed to make a judgment call after a few steps as far as which one of these you'd like to use. I will demonstrate this with an example in the next video.